let's take a look here at chapter number 6, which is what we just finished. In chapter 6, we looked at the periodic table, the modern periodic table, the blocks of the periodic table, and the periodic law. Of course, when we talked about this, we were explaining the periodic law. First off, what is the periodic law? What is the significance of it? Why does it matter? The periodic law is simply a way of saying that we expect to see repeating characteristics as you move down a group in the periodic table. And we can make accurate predictions for the periodic table based off of where they happen to be in what group. And a lot of the work done for this, the way that we see the periodic table now, was done largely by Mendeleev. Gets most of the credit. Mendeleev ends up being the guy who we remember for a lot because of the way that he organized. He organized them by mass, by atomic mass. And the reason why his was significant is because he left gaps in the periodic table. And these gaps in the periodic table were for things that had not yet been discovered. And amazingly enough, people found the stuff and it fit right into a lot of what he had done. So Mendeleev kind of gets credited as sort of the guy who orchestrated the most modern version of it. Certainly it's been a work in progress by many men, many people. Shouldn't say just men. There was certainly some women in there who played a very significant role. But ultimately, Mendeleev kind of gets the credit for the way that we see it laid up now, by order of mass. And then, let's see, what did we talk about after Mendeleev? We really then took a close look at the phases. We looked at phases. And what we saw with the phases on the periodic table is the vast majority is solids of a variety of many different types, largely metals. A small percent, a few of them are liquids. And oops, that's not true. Few of them are gases, excuse me. And how many of them are liquid?
2.
Only 2 are liquid. And of course, we identified those in class as mercury and bromine. Those are the ones that end up at room temperature, at room pressure, at standard temperature and pressure. Mercury and bromine are the only 2 that exist as liquids. By the way, I'll go ahead and tell you that's not one of the test questions. What are the 2 liquids? I'm going to ask you a little bit more detail than that. But then really where we kind of went off on this chapter where we spent a lot of time was talking about this 4 blocks. The 4 blocks of the periodic table explain so much about how it works. So we have the S block, we have the P block, we have the D block, and we have the F block. And the idea is that the S orbitals, we said, can hold a maximum of 2 electrons. And lo and behold, the S block ends up being 2 groups of electrons, 2 groups of atoms. Not at all a coincidence. The P block can hold a maximum of 6 electrons, so therefore it has 6 groups. D, of course, is 10, and 14. We, of course, see an obvious pattern that forms. The number of groups that block represents on the periodic table, that's vertical columns, is directly related to how many electrons that orbital, that block, can hold. Right? So you should be reasonably familiar with where the S, P, D, and F blocks are. I know we've had a lot of different periodic tables we've looked at. Those are significant. And really, the last topic then in Chapter 6 is the idea of trends. And really, the trends really kind of all revolve around this idea of atomic radius. And the overall trend for atomic radius is we said that as you go right, generally we expect atomic radius to decrease. And as you go down a row, or down a column, we expect them to increase. A great question there, or two things that you're going to be asked to know about, is first off, I want you to be able to apply this. So just like we did in class where I gave you a handful of elements and said put them in order from least to greatest, I'm going to ask you to do that on the test. So you'll have to be able to use some sort of useful strategy to make a logical explanation of which one's biggest and which one's smallest and which ones fall in what order. I think there's, 4 or 5 that you're going to have to put in order. But then really the question is why? Why do they change their sizes? Well, atomic radius decreases because of the stronger nucleus, and the atomic radius increases going down because you are adding another layer, adding a new energy level. So of course, if you're adding another energy level, you're talking about these are going to be expanded out significantly. That's going to be a big jump, big bump out in space. So the atom is going to be significantly larger in that way. And kind of piggybacked on this idea of atomic radius, this trend on atomic radius, is the idea of how it fits in with what we call ionization energy. Ionization energy is something where we're talking about the amount of energy necessary to strip one of those electrons off. And of course, if we're going to tear an electron off, you're going to end up with something called an ion, which is going to be something that is going to be a charged isotope. Or charged atom, however you want to look at it. It's going to have some sort of a charge, be it either positive or negative, and that's all due to a change in the number of electrons. And the idea is that if you are talking about figuring out how you're going to strip those electrons off, we look at, say, for example, at lithium. Lithium is a good example of this. Lithium has an atomic number of 3. So that means it has its 1s orbitals filled, and then we have the 2s. There's only one electron out there. And so that one electron that is out by itself in the 2s is very easy to extract away. It takes little ionization energy to pull this away. So what we can say is that when we have fewer electrons in the valence layer, it's easier to pick those things off. It doesn't take as much energy to do that. Which is why lithium is very useful in one particular application today. Does anybody know what we'd use lithium for? You stick it inside something that we use. I'd be willing to bet all of your iPads are using a large one of these.
Batteries?
Battery, right. A lot of them are used in some sort of lithium-ion battery of some variety. I don't know exact composition of it. I would guess they're lithium batteries. That's inside of the iPad. Or at least a lot of batteries use this because it doesn't take much energy to pop this electron off. And then we have those electrons coming off of there, which gives us a nice stream of electricity. So that's part of the appeal there, that the ionization energy does not take very much. And on that note, that is the end of what we should know from Chapter 6.